Hello everyone. In the previous video we talked about eigenvalues, eigenvectors, how we calculate them, and the characteristic polynomial. In this video we are going to talk about eigen-decomposition and properties of eigenvalues, and hopefully, if time allows, we don't want to make super long videos anymore, applications of eigenvalues. Otherwise I'll talk about them in a separate video. So first, if a matrix is real symmetric matrix, all eigenvalues are real. So we can show that if a matrix has all real entries and it's symmetric, then all eigenvalues are real. And you might be asking me, are there matrices that the eigenvalue of which are not real numbers? And the answer is yes. Okay, here I give you an example. So all I need here to make life simpler is to let's say here it is going to be lambda minus 1 squared, and then all we need is to add something to it. So maybe we add a -2 here. And now if I just run this only, you can see here that if you look at the matrix, so the matrix A was 1, -2, 1, and 2. And if you look at the eigenvalues, they are complex numbers. And if you look at the eigenvectors, they are also complex numbers. Okay, so there is no guarantee that your roots of the characteristic polynomial, which is an nth order polynomial, are always real numbers. They could be complex numbers. But here, this tells me that if it is symmetric with real numbers, then definitely eigenvalues are real. So if I go back here, and this is 1, -2, correct? If I make this a -2 and let's say 3, now the diagonal here is 1 and 3, and the anti-diagonal is -2, 2, -2, -2. So it is a symmetric matrix. Now, if I do it here, then definitely my eigenvalues are going to be what? Real numbers. It doesn't say if they are positive or not, but it says they are what? Real numbers. So keep in mind, and there is proof behind it, but again, we are not going to be after proofs. So now, this eigen-decomposition theorem says, if you have a matrix which is symmetric, which means eigenvalues of it are real, and here we assume that really the numbers we are selecting for the entries of the matrix are real numbers, then it says your matrix can be written as, matrix M, can be written as the product of 3 matrices, Q, D, and the transpose of Q, where D is a diagonal matrix. The diagonal entries of this diagonal matrix are the eigenvalues of M, and Q is an orthonormal matrix. Orthonormal matrix is a special type of matrix. Please watch our other video where we talk about orthonormal, orthogonal, and other types of matrices like positive, definite, positive, negative, semi-definite, and so on. But orthonormal means a matrix that has columns that are perpendicular to each other. So each column is perpendicular to all other columns. And then the magnitude of each column is 1. So all columns are unit vectors, and they're all perpendicular to each other. If a matrix is orthonormal, like the rotation matrices that we have in robotics, then you can show that the transpose of the matrix and the inverse of the matrix are the same thing. Okay, and also like the determinant of the matrix is +1 or -1. So the matrix Q is an orthonormal matrix, columns of which are what? Eigenvectors of M. So let's say if this A has, let's say this A is, for example, a 2 by 2. Then it has two lambdas, lambda 1 and lambda what? 2. So if you want to write it as A, write it as Q D Q transpose, then what's going to be D? What's going to be your Q? So your D is going to be a diagonal matrix with lambda 1 and lambda 2 on the diagonal, everywhere else, of course, 0. And then your Q matrix is going to be two vectors, and they are what? V1 and V2, the eigenvectors corresponding to lambda 1 and lambda 2. Each one of these vectors is a 2 by 1, so Q is going to be a 2 by 2. Okay, so you can write matrix M like that. And what's the good thing about it? The good thing is, by the way, this kind of decomposing M as QD, Q transpose, we call it the Eigen-Decomposition of M. What's good about it? I'll show you. It has so many advantages. First of all, M is now written as a diagonal matrix times 2 orthonormal. So this is called diagonalization also of M. I mean, we can convert M to a diagonal, not that M is a diagonal, but if you look here, your M is equal to Q D Q transpose. So if I want the D, the diagonal equivalent of M, all I need is to multiply from the left side by Q transpose, from the right side by Q. You know, Q transpose and Q inverse are the same thing. So basically you can show that you have Q transpose M times Q is going to be D. So by multiplying M from left side by Q transpose, right side by Q, I can convert it into what? A diagonal matrix. So this thing is called diagonalization of M. And if I can do such thing, we say M is diagonalizable. Now, if we want a matrix to be diagonalizable, it has to have either distinct eigenvalues, which means distinct eigenvectors, or it has to be symmetric. If a matrix is symmetric, although it might not always have distinct eigenvalues, but it will have distinct eigenvectors. Okay, so if a matrix is symmetric, then it can be diagonalized. Okay, now let's exactly take a look with an example, right? Instead of just talking about theories, let's take a look at an example. So in this case, my matrix was symmetric and we have V and D. Now the question is, if I say, if you look, this V matrix is the same as Q, right? The matrix V, not vectors V1 and V2. The matrix V is the same as what? Q, right? Because the first column of it is V1, the second column of it is V2. So this is V, this is what? And this D is a diagonal matrix. The diagonal entries of each are what? The eigenvalues. So the question is this. If I say, just like this decomposition, if I say QD Q transpose, in this case VD V transpose, so V times D times V transpose, what is that? Is that the same as A? And of course it is. You see, so I can write A as what? As the Q, which in this case is the same as matrix V, and D and V transpose. So if you want, when you do the eigenvalue decomposition, instead of calling it V and D, I can call it what? Q and capital D. And now I say what? What is Q times D times Q transpose? And you see the answer is the same as what? A, right? And as I said, if you go the other way around, so say Q transpose times A times Q, what's the result? It is going to be the diagonal matrix. where the diagonal entries of the result are what? Are those eigenvalues. Okay, so by multiplying Q transpose by A by Q, I can definitely convert my matrix into what? A diagonal matrix. Okay, so A is diagonalizable. And okay, fine, it is diagonalizable. What's the benefit of being diagonalizable? So it's symmetric, it's diagonalizable. I know how to diagonalize it. I know eigen-decomposition, fine. Now, what's the point? Well, the point is this. If I say, could you calculate for me A squared? Right? Let's calculate the power of A. So I can write A as Q D Q transpose. And I know that Q is an orthonormal matrix, so Q transpose is the same as what? Q inverse. Good. So if I say what is A squared, what would you say? You say that means A times A. Fine. Now let's plug what we know for A. Let's plug it down here. So it's going to be Q D Q transpose times Q D Q transpose. So what would you get? You can here multiply these two matrices together. And what would you get when you multiply? Well, Q transpose Q, remember transpose is the same as inverse. So this is going to be the same as Q inverse times Q. And Q inverse times Q is what? Identity matrix. And you know, identity multiplied by anything is the same thing as it was. I has no effect. So the result of that is going to be what? Is going to be Q D times Q transpose. And what is D times D? D is a diagonal matrix. You can write it as what? D squared, of course. So you can write it A squared as what? Q D squared Q transpose. And the good thing is D squared is very easy to calculate because D is a diagonal. So if D is a format what? As I said, lambda 1, 0, 0, lambda 2, it's a diagonal like this, then what is going to be D squared? D squared is the exact same shape as D, except these lambdas are going to be squared. And you can easily check that. Just multiply this by itself, you're going to get the elements squared. If it's power 3, D cubed is going to be lambdas cubed. D to the 4, lambdas to the 4. D to the negative 1, lambdas to the negative 1. D to the 1/2, lambdas to what? To the 1/2. So in general, you can write any power of A as what? Q D to that same power of A times what? Q transpose. And this Dn is the same as D, except these lambdas are going to be what? To the power n. So this way, you can calculate any power of A a lot easier because Q and Q transpose are calculated once, or just Q, let's say, because transpose is not really such a sophisticated thing. So once I know Q and once I know D, raising each entry on the diagonal of D to the power that I have is not a hard thing, and multiplying by Q and Q transpose is not a hard thing. So instead of me multiplying A n times by itself, I can just follow this simple formula and calculate what? Any power of n. And this makes my calculations of power of n very, very easy and possible. So if somebody says, okay, what is the square root of A? Right? You say, well, the square root means Q D to the 1/2 times Q transpose. And D to the 1/2 means the diagonal entries, which are the eigenvalues, are the square root of them. Right? Or if somebody says, what is A to the negative 1? You say it is Q D to the negative 1 Q transpose. And this might be an interesting thing if you look. You know, A inverse is A to the negative 1 is inverse of the matrix, right? If you look at this, this is what? This is a diagonal matrix where if, let's say it's 2 by 2, the diagonal entries are 1 over lambda 1, 1 over lambda 2, right? Because it's like lambda 1 to the negative 1, right? Which is 1 over lambda 1, all the way to 1 over lambda n. So what does this tell you? this tells you something really nice. It tells you the eigenvalues of A inverse are what? Are the reciprocals of eigenvalues of A. And that's this theorem that you see here. That the eigenvalues of A inverse are the reciprocals of what? Eigenvalues of A. And that is what? Very, very nice. Some other theorems, it says like eigenvalue of A and A transpose are the same. They are, because if A is Q D Q transpose, what is A transpose? Well, A transpose is the transpose of that whole thing. And you know, when you apply transpose to a product, it's going to transpose each and every one of them, but reverses the order. So it's going to be transpose of this one. Transpose of transpose is Q itself. It's going to be D transpose, and this is going to be Q transpose. And since D is a diagonal matrix, transpose of it is the same as D. So it's going to be what? Q, D, Q transpose. Look at that. I wrote A as Q, D, Q transpose. A transpose is also written the same way. So what does it mean? It means the eigenvalues of A are the same as eigenvalues of what? A transpose. And that's what you see here. Right? So transposing a matrix is not going to change the eigenvalues. Taking inverse of a matrix will make the eigenvalues what? To be reciprocal of the original ones. Look at this one. Determinant of a matrix is the product of the eigenvalues. It is. Why? Because if I say what's determinant of A from here, is going to be the determinant of Q, D, Q transpose. Determinant of product is product of determinant. So it's going to be determinant Q, determinant D, determinant Q transpose. And remember I told you Q is an orthonormal matrix, means the determinant of it is 1 for a right-handed system. The same for transpose. So you see the determinant of A is going to be the same as determinant of D. And D, remember, it's a diagonal matrix with lambdas in it. Correct? So what's the determinant of this matrix? You know, determinant of a diagonal is what? The product of the lambdas. There we go. So determinant of any matrix is what? The product of the eigenvalue. So that's another use of eigenvalues. If somebody now says, hey, what's the determinant of A? Look at it. It's -1. Now, what if I multiply these two eigenvalues by themselves? So basically, I need D11 and D22. Look, D11, the first eigenvalue, times D22, the second eigenvalue. Here we go. You see, the product of eigenvalues is the same as what? Determinant of the matrix. Right? And you can see that. Right? Or here, when I said the Eig, instead of saying Eig, I say what's Eig of inverse of A? What are the eigenvalues and eigenvectors of inverse of A? Look at that. The eigenvalues are these two numbers. What was the ones for A? They were these guys. Let me find them here. -23.6, 423. -423 and 23.6. And these numbers are the inverse of those, because if you divide 1 by 0.236, 1, that's the other number. Okay, this third and fourth decimal changes is because this number is not exactly 0.2361. It's only that number up to 4 decimals. Okay, so you see clearly it works. Or let's say here I said a to any power. So let's say I want to calculate a to the power 3. So I can say a cubed, right? This is one way to do it. The other way is I can say q times what? Times d cubed times q transpose. Right? Just raise the elements in d to the power 3 and multiply from left and right by q and q transpose. Now look at the numbers. Are they the same? Well, let's make sure that I did not make any mistake, which I don't think I did. So A is this. I changed it, that's why. They are eigenvalues of A. There we go. So now again, A cubed is this, and QD is cubed, Q transpose is this. And now if you compare them, they are the exact same thing, right? So instead of calculating A to the cubed, I do this. And this one takes a lot less calculations compared to A cubed. Computationally, it's way more efficient to do it this way than this way. Okay? And I can show you by calculating how many operations each one needs. But this one is a lot faster and easier than this one is. So this Eigen-Decomposition is a very powerful tool. It can convert your matrix into a diagonal, and diagonals are very easy to deal with. Raising them to any power, finding their determinant or anything. So if you can convert your matrix by a pre and post multiplication by an orthonormal matrix Q, that makes further matrix operations a lot easier. So hopefully this so far made any sense to you. Now let's take a look at some other things, but before that, let me clarify the rest of the stuff too, because I just explained them. So remember, I told you eigenvectors of a symmetric matrix corresponding to distinct eigenvalues are orthogonal. So that's why you can diagonalize a symmetric matrix. I also told you that if you can write M as a diagonal, then M inverse is QD to the -1, Q to the -1, and this Q to the -1 is the same as Q transpose. So this is any power of Q, and I also mentioned it here for you, that other powers of any power, any fraction power of negative, positive of a matrix can easily be done once you write it into this Eigen-Decomposition form. Now, a couple of other important things about eigenvalues. One is trace. Remember, trace was sum of the diagonal elements of any matrix. It says that's equal to the sum of the eigenvalues. That's interesting, right? Determinant was product of eigenvalues. Now it says trace is sum of the eigenvalues. So that's interesting, right? Let's go. So A was this. Trace here is what? There is a command trace in MATLAB. It's 1 plus 3, right? Sum of diagonals. That's what? That's 4. And if I look at sum of the diagonal, sum of the eigenvalues, which is D11 plus D22, that is also what? 4, correct? So sum of the eigenvalues is the same as what? Trace of A, okay? And there is proof behind it, but again, we don't need to do that. Finally, it says rank of a square matrix is the number of non-zero eigenvalues of A. So if your matrix A is n by n and it has, let's say, m eigenvalues that are non-zero, they are not equal to 0, that's the same as rank of A, right? So in this case, my matrix has no eigenvalue of 0. This is 1, the other one is this number. None of them is 0, which means what? I have two non-zero eigenvalues, so if I say what is rank of A, it is going to be 2, right? But if one of these eigenvalues was 0, then rank of A would be 1. Or the determinant of that would be 0, because determinant is the product of eigenvalues. If one of them is 0, it means what? It means the determinant is 0. And you know, when determinant is 0, not all columns are linearly independent, which means the matrix is losing rank or it's rank deficient, which is exactly what you can see in this theorem. Okay, so these are some very important properties of eigenvalues and the eigen-decomposition. Now that we have some time, let's talk about some of the applications of these eigenvalues. So I told you about powers of a matrix. Some other things that you can see is one of them is axis angle representation of a rotation. So if you rotate a vector v around the unit vector k with angle theta and get a rotated version of v, which we call v rotated, right? This rotation going from v to v rotated is given by what we call a rotation matrix R of k and theta in robotics, which is called the Rodriguez formula. And sometimes I'm not going to give you k and theta and v and ask for v rot. Sometimes I do the opposite, actually. I give you v and I give you v rot, and then I ask what is k, what is theta. So I give you the initial vector, the rotated vector, and I say about what axis and by how much of angle I have rotated it. And one way to calculate it is if I give you a rotation matrix, which you can calculate from v rotated and v, so you calculate the rotation matrix from these, then the rotation matrix, you can show that when you apply it to the vector k itself, the result is going to be 1 times k. The result is not going to be any different than k. So basically, if you have an axis in a rotation, if you rotate that axis itself about itself, of course, it's going to be the same as what it was. So you can show that one of the eigenvalue, and this is, if you look, this is exactly an eigenvalue problem. R is the matrix, k is the vector, lambda is 1. So you can show that one of the eigenvalues of the axis angle presentation is 1, and then it has 2 other eigenvalues, because this matrix, rotation matrix in general, is a 3 by 3, so it has 3 lambdas. One of them is 1, and it has 2 other lambdas, and those 2 lambdas always form a complex number, pure complex number, like e to the I times theta, and the argument of that is going to be what? The angle of the rotation. And this lambda of 1, it corresponds to an eigenvector v1, and you can show that v1 is the same as the unit vector k. Okay, so by solving eigenvalue problem for a rotation matrix, you can find the axis of rotation and the angle of rotation equivalent to that rotation matrix. Please watch my video under robotics for axis angle representation, and you'll find about this. Okay, so this is one of the places that you'll see axis angle representations. Another place that we talk about eigenvalues are vibration problems and natural frequencies. Okay, you can easily show that in a multi-degree of freedom system. Let's say, for example, if I have a system like this, I have a 2 degree of freedom system. So I have a cart number 1 here, and it is attached by a spring to the wall. This is K1, this is M1, is attached by K2 to M2. And maybe this K2 is also attached to another wall by K3. So here, if you call the motion of each one of these blocks x1 and x2, and you give it some initial displacement and let go, the system starts oscillating. It's going to have 2 natural frequencies, and those frequencies, they can be determined through eigenvalue problems. Because in this case, if you write your equations of motion will be like m1 x1 double dot is going to be equal to k2 times x2 minus k1 plus k2 times x1. You can check my equations later. And m2 times x2 double dot is going to be equal to k2 times x1 and then minus k2 plus k3 times x2. Okay, these are the governing equations. And if you rewrite this into a matrix format, by considering that the solution here is going to be harmonic, so x1 is going to be some magnitude a times sine omega t, and x2 is going to be another coefficient b times sine omega t. Okay, if you plug them in, then it means x1 double dot is going to be negative omega squared a sine omega t, which is going to be negative omega squared times x1. And you can show that x2 double dot is also going to be negative omega squared x2. So if you form x1 and x2 into a vector x, then your vector acceleration x double dot is going to be negative omega squared times vector x. Okay, so if the solution here is harmonic, which you can show, that's the only solution possible to such set of equations. So if you plug it in up here, you will get negative omega squared x, right, is equal to, and of course there is m1 and m2, so if you want to write it, you have to write it like this. Negative omega squared m1 0 0 m2 times x. This is equal to, and then on the other hand you have something times x again, and that something is gonna come from these coefficients, so it's gonna be negative k1 negative k2. That's going to be k2, this is going to be k2, and negative k2 negative k3. Okay, so this is going to be your system of equations. And now what you can do is you can bring so if you call this a K matrix, and if you call this the M matrix, so this is called the mass matrix, this is called the stiffness matrix, what you can do is you can multiply both sides by M inverse, then you'll get what? Or by, M inverse is good. You will get negative omega squared x is going to be M inverse K times X. And now if you call this matrix A and call this constant lambda, then you'll get what? You'll get A times X equals lambda times X. Yes? There is only, let me make sure, there is no caveat. No, it all looks good. Negative, negative, that's all right. One thing I can do is to get rid of that negative, I multiply both sides by a negative M inverse. That way this negative and that negative go away, so here you get a positive, here you get a negative. And that negative, you can call that whole negative M inverse K, you can call it the A matrix, or you can apply the negative to the elements in K. So if you negate these elements, that's going to be negative K. right? And so now if you look, this is clearly an eigenvalue problem, where lambdas are what? The square root of the square of natural frequencies. So lambdas are what? Lambdas, which are eigenvalues of A. And what is A? A is negative M inverse K. These are the square of natural frequencies of the system, frequencies of the vibrations. So if somebody says, what are the frequencies of vibrations in this system? All you need is to find the mass matrix, to find the stiffness matrix, multiply negative M inverse by K, call it matrix A, and then find the eigenvalues of it, and then what? Take the square root of that. That gives you the two natural frequencies. And if you plug it back here, it gives you vector x's. And vector x in vibration, we call it mode shapes. So here x is in vibration, we call x the mode shape, and lambda equals omega squared, where this omega is the natural frequencies. There are two omegas, so there will be two natural frequencies. Okay, and you can watch videos related to free vibrations, which is this kind of problem. The system subjected to initial displacement without any external force. Finding the natural frequencies can be done by an eigenvalue problem once you have matrix A. Okay, there are other applications in engineering. There is one thing called manipulability, which is defined for a robot, and how close the configuration of a robot is to a singularity. Please watch my video under robotics playlist for manipulability. And over there, you see that we use this matrix called Jacobian matrix of the robot. And you'll see that there is something called the manipulability ellipse, which shows in which direction my end effector of the robot can move a lot, in which direction it can move a little bit. And these two directions that my end effector can move the most and the least are the eigenvectors of the Jacobian matrix. Okay? So you can watch that. I'm not going to go into detail of that. I told you about natural frequencies, and finally something maybe related to your statics or solid mechanics are principal moments. So if you remember in your statics or solid mechanics, you calculated the moments of inertia or the moments of surface for any arbitrary surface. So if this is a surface and I have the x-axis and the y-axis, correct? If you remember, and the area was A, you could calculate Ixx, you calculated Iyy, and you calculated Ixy, correct? These are the entities that you calculated in statics. So this was basically the integral over surface of y squared dA. This was the integral of x squared dA, and this was the integral of xy dA, correct? The product moment. So if the surface is not symmetric about x and y axis, then this product is not zero, and what you will get is an inertia matrix, which is like this: Ixx, Ixy, Iyx, which is the same as Ixy, and then Iyy. So you will get a symmetric matrix I 2 by 2 for a two-dimensional problem. And it is not diagonal because these products are not zero in general, right? But if you remember in statics, you had something called principal axes, and those were the axes that they are rotated with respect to the original coordinate system. So if you rotate about these axes, call them x prime and y prime, in the x prime, y prime coordinates, the product term was zero. So all you had for the inertia matrix was a diagonal matrix, correct? It was I x prime, I y prime, and 0 and 0. So those set of axes for which the product was 0, if you remember, we called principal axis, and we calculated some angle phi for them based on these three terms. And we could also calculate these principal moments, correct? If you remember, you had the square, you had some formula in general, which was, or you did the Moore circle, if you remember, or instead of the moment of inertia, this could be the stress tensor or the strain tensor. And for that matrix of stress, strain, or moment of inertia, you could calculate the principal axis, and we could calculate the angle and everything, and we had analytic formulas, and we had the Moore's circle, if you remember. And this is what you had in statics and solid mechanics, correct? We had a formula, as I said, for phi, and then a formula for calculating the principal moments or the principal stress, correct? Sigma max and sigma min, let's say, right? And then tau max and so on. So one way to do it is using eigenvalues and eigenvectors. How do I find the direction of these, x prime and y prime? Well, it's not really hard to show that the x prime and y prime are the directions of the two eigenvectors v1 and v2, where v1 and v2 are eigenvectors for which matrix? For the I matrix. So this I matrix has two lambdas, and it has what? Two v's, correct? Two eigenvalues and two eigenvectors. And the eigenvectors are showing the direction of x prime axis and y prime axis, the principal axis. Right? Just like that. So if you did it by the Moore circle or by the analytic formula, where it was calculated based on angle, and then you took derivative with respect to angle, set it equal to 0 to give you the angle of the principal axis or anything. Another way to do it is simply by doing a eigenvalue problem. Let me show you a numerical example here. So here I'm gonna do it on a stress tensor or a stress matrix. So here is a 2D example, and these are the stress along x and y, normal stress, and the shear stress xy is 15, 15. So I'm looking into principal axis along which I only have normal stress components and no shear. If you remember from solid mechanics, the way to calculate the angle of the principal axis, x prime with respect to x, was 1/2 tangent inverse of tau xy over the 1/2 of the difference between sigma xx and sigma yy. If I go ahead and apply that formula here, right, it is going to be 1/2 tangent inverse of, this is 60 divided 30, 15 that, it's going to be 1/2. So it's going to be 1/2 tangent inverse of 1/2, right? And let's do that here. So 0.5 times a10 d of 0.5. And the answer is 13.28 degrees. So 13.28 degrees, if I rotate my stress element, so this is my stress element, this is sigma yy, this is sigma xx, this is tau xy and tau yx, which are the same thing. If I rotate this element by 13 degrees, so I rotate it like this, where this angle here is 13 degrees, then on this new version, this new rotated version, I should only have sigma x prime and sigma y prime, and the tau on each one of these planes should be 0, right? So that angle is called theta p. Now, how can I find it? Can I use my eigenvalues and eigenvectors? So let's do that. So here I say my A matrix is equal to 100, and then 15, and then 15, and 40. And give me the eigenvalues and eigenvectors for this. It does. So these are the eigenvalues and the eigenvectors. If you look at them, one of them is this, the other one is this, right? Now the question is any of these gonna give me the angle of 13 degrees or not? So 1328. First of all, which one should I look? So since I'm looking into maximizing sigma x prime, right? This is where the x prime becomes max. So this one is equal to sigma max. Therefore, I should look into lambda max. And lambda max is here, the second one. One of them is 36, the other one is 103. So I'm going to look into the one corresponding to 103, and that's this negative 0.9732 and negative 0.2298. Now the question is the slope of this guy also 13 degrees something? Let's find out. So I say, what is arctangent d of negative 0.2298, the y component over the x component? And I can get rid of the negatives because they both have negatives. And 9732. And guess what? I get my 13.28, which is what I had here. So clearly you see that a simple eigenvalue problem, the eigenvector corresponding to the largest eigenvalue, the angle of which is exactly also what? Theta p. Okay, so what you did using the Mohr circle, as I said, all the analytic formula that I showed you over here, can also be done by the eigenvalues. So these eigenvalues have lots of applications from math. By the way, these powers of A, we use them in controls a lot. When we go to controls of MIMO systems, we definitely need to work with a matrix A, which is called the state transition matrix. And we have to look at the powers of that sometimes, or functions of that. This axis angle is robotics, manipulability is robotics, principal moments are statics and solid mechanics, and natural frequencies are vibrations. So I showed you some applications of this topic in several undergrad or graduate level courses. So hopefully the video was useful to you, and I will see you in my next video. Thank you.